Alright, so this video is part of a compilation of videos I've done on Epsilon-Delta proofs, and if you want to see the full compilation, there's a link down in the pinned comments below. But I hope you love this standalone video just to digest this one proof, and I'm excited to bring it to you right now. Alright, so we have the last limit now. I want you to try to really be creative and play around with this, and then we can do it together, okay? So if you haven't already, consider pausing the video, working this out, or even pausing at individual steps if you need a kind of push forward. So we're gonna get limit x goes to 9 of root x minus 5. Again, when x is exactly 9, because this is a continuous function and x is 9, you get the square root of 9 minus 5, which is 3 minus 5, which is equal to negative 2. Okay, so that's going to be our limit value, and now we have to rigorously prove it. So I'm just going to steamroll through this. We want the absolute value of root x minus 5, so root x minus 5 minus of negative 2. Okay, so that's going to be plus 2. Okay, so minus of negative 2. I'll just write it in 2 steps. We want this to be, if I give an epsilon, or let's reverse the roles. If you choose an epsilon so that you want this to be less than epsilon, you want root x minus 5 to be sufficiently close to negative 2, my job is to find a delta so that if the absolute value of x minus 9 is less than delta, then I can ensure that. Okay, so if x is sufficiently close to 9, I can ensure that. How close? We need to figure that out. So we need to solve for delta as usual in terms of epsilon. So now we can write this. We need to somehow write this expression in terms of x minus 9. Okay, that's going to be slightly tricky, but the same idea as before, but slightly different. So you're going to get root x minus 5 minus 2 is going to be, it's going to be root x minus 3. We want this to be less than epsilon. Okay, now how do I write this in terms of x minus 9? Okay, so that's going to be slightly subtle. Basically, the point is that you can't really factor an x minus 9 into it. So you have to kind of do what we do with limits if you have like radical limits, which is you want to multiply top and bottom by the conjugate. So here we have root x minus 3. So if you multiply root x minus 3 times root x plus 3, okay? So you do that, okay, and that's the difference to get to x minus 9. Okay, we want to get rid of the radical because we want to find an x minus 9 in here. We need to get rid of the radical, and whenever you do that, you use the difference of squares formula. So you multiply by the conjugate. Root x minus 3 times root x plus 3 is going to be root x squared, which is x minus 3 squared, which is 9. Okay, so therefore you know that root x minus 3 is equal to the absolute value of x minus 9 divided by root x plus 3. That's going to be the expression, and we want that expression to be less than epsilon. Okay, so how do we ensure that that's less than epsilon? What does delta have to be? So I want you to pause it. If you haven't already done, pause it here and try to work it out. Okay, and then we will get to the next step. Okay, so I'm just trying to help teach you. I'm not looking for more watch time or anything like that. I just want to help you to learn, and so if you pause it and try to work it out and you're confident with it, I'm really happy. But let's actually just now get to it. So we've got this. So we've got absolute value x minus 9 by root x plus 3. So we know we can make absolute value x minus 9 small. Okay, that's our job, is to find out how small it's got to be. We have that power. We can make it as small as we like. But the root x plus 3 we don't quite know. So we multiply this by 1 over root x plus 3, or the absolute value of that. So we want to say that this is less than epsilon. So if we make x minus 9, so we have the power to make it as small as we like. So same game, let's say that we make x minus 9, absolute value of that to be less than epsilon times the absolute value of root x plus 3. Okay, let's say we do that. Now if we can do that, right, if we do that, then we are ensured this expression is less than epsilon. But the same difficulty applies. This is not right. Okay, I'm always emphasizing this is wrong. But we just have to figure out how to write. Our delta cannot be this. It has to be in terms of only epsilon. Okay, so we need to look at our root x plus 3. All right, so let's kind of try to understand what has to happen here. So if our x is exactly equal to 9, then we would have to take our delta to be 6 times epsilon. Right, if x is exactly 9, you get square root 9 plus 3, which is 3 plus 3, which is 6. So then we'd get a 6 epsilon. Okay, so that's all well and good, but remember we can't really do that because x can be slightly less than 9, slightly more than 9, right? So, but the thing is this, if x is just a little bit less than 9, we need our delta to be smaller. Okay, so imagine our number line, our 9, we go from something to something, okay, some range of 9. Okay, now we know that if x goes to the right of 9, then our root x plus 3 is going to get larger. Okay, so that means that we don't need our delta. 6 epsilon is fine for our delta. Okay, we'll get something higher than 6 times epsilon is what we need. So 6 epsilon will be better than what we need. But if our x goes to the left of 9, then we have an issue. Okay, now I want to make things nice. I don't like taking the square root of 8 or something. So here we're not going to take delta equals to 1. Okay, we can actually, but we're not going to like be very precise there and take the precise maximum value of root x plus 3 on the interval from 8 to 10 or something. We're just going to observe, or the precise minimum value of it. Okay, we're just going to observe that root x plus 3, the worst case is say when x is 4, that's the closest perfect square to 9. When x is 4, then basically we get root 4 plus 3, which is 2 plus 3, which is 5. So then we're going to get 5 epsilon. Okay, so let's just take want our delta to be equal to 5 epsilon. So we want it to be less than or equal to 5 epsilon, and we also want it to be small enough that it's within the range of 4 to whatever. Okay, it doesn't matter what we go to the right, but we want our interval to be symmetric, so 4 to 14 or whatever. Okay, so we can just take our delta to be less than or equal to 5 epsilon, and we have the power to make delta as small as we need to ensure our end expression is less than epsilon. So we can take our delta to be less than or equal to the minimum of 5 epsilon, and let's say 5. Okay, we could also take 1. It doesn't really matter. We can take 1, 2, 3, 4, 5. We can't take 6 because then we'll get a smaller number than 5, and then we need our delta to be even smaller. So let's take the minimum of 5 and 5 epsilon, and let's then write our proof. And this is just the last one. I'm going to write it out very precisely to really help consolidate it for you. It's been a marathon. It's been fun. I've actually been recording for an hour on this. All right, so let's get into our epsilon delta proof. And here it's kind of going to be looking blind. I'm not going to actually show what we just did. I just erased it. So let's get into it. So let epsilon greater than 0 be arbitrary. And now we want to say that we want to pick our delta. Okay, so let delta equal to the minimum of 5 and 5 epsilon. Okay, it didn't really matter, as we said. It could be minimum of 1 and 5 epsilon, that would have been fine. 4 and 5 epsilon, that would have been fine. So let delta be that. So if the absolute value of, okay, the x minus 9, because we're taking limit as x goes to 9. So if absolute value x minus 9 is less than delta, then we know that the absolute value of this expression, root x minus 5 minus 2, okay, which is going to be root x minus 3. Okay, that's going to equal to the absolute value of x minus 9 divided by the absolute value of root x plus 3. Okay, that's going to be the expression. And x minus 9 by root x plus 3, that's going to be, well, we know that the x minus 9 is less than delta, right? And delta is the minimum of 5 and 5 epsilon. So again, it's the same kind of order. The first step we're going to use to handle the x minus 9, we're going to use the fact it's less than 5 epsilon. So we're going to say that delta is less than or equal to 5 epsilon. Delta is less than or equal to 5 epsilon, but absolute value x minus 9 is less than delta. Okay, so we know that it's going to be less than 5 epsilon. So you get 5 epsilon here. And then secondly, we know that delta is less than or equal to 5 because it's a minimum. And because delta is less than or equal to 5, we know that the minimum value of root x plus 3 on the interval 4 to 14, right? Because we're looking at an interval around 9, x minus 9. So again, I write 4 to 14. We know that root x plus 3 is at least the root 4 plus 3, which is at least 5. So therefore, if you take the reciprocal, it's less than 1 over 5. So we're going to get a 5 on the denominator. That's going to be equal to epsilon. So that's our epsilon delta proof. And yeah, it's been really fun. It's been a marathon. I got my COVID booster recently, so I'm really tired for some reason. I think that's probably the reason. I feel like I'm going to fall asleep, but I love making this video. It was a lot of fun, and I hope you loved it too. And please don't forget to check out a lot of other fun content on my channel you're going to love. Please don't forget to like and subscribe. And again, please consider subscribing on Patreon if you're really enjoying my content. Every little bit helps and makes a huge difference to my channel, and I'm so grateful to all the support. Thanks so much to Alex and Nathan. Here's a fun proof. If you really enjoyed this video and enjoyed learning these analytical ideas, a proof that an increasing function that is monotonic, okay, an increasing function, it's going from R to R, has to be continuous almost everywhere. Okay, it cannot be continuous at discontinuous at a lot of points. Check that out, it's gonna pop up on the screen here. And for another fun video you're gonna love is a number theory proof. Okay, it's about harmonic numbers. It's connected to the Riemann hypothesis. It's so lovely, you're gonna love it. It's a really simple and elegant number theory proof. Check it out, it's gonna pop up on the screen here. Wish you an amazing day. I'm super excited to see you in either of those videos. Wish you a great year ahead. Hope you ace all your exams, and I hope this video was really helpful. And if you watched this far, please drop a comment down below. It means so much if someone watched this far and got to the end and saw this whole video, and really if it helped you master epsilon delta proofs. Catch you later, and I wish you all the best.